I've identified 7 recurring techniques that you can use to solve the vast majority of string-related problems on the technical coding interview. In this video, I'm going to go over them at a high level, but in future videos, I'm going to go technique by technique and take a deeper dive with a focus on intuitive understanding. So let's get started. The first technique that I want to talk about is linear time string matching, LTSM. There are a few algorithms for doing linear time string matching, but the most common one is the Rabin-Karp algorithm. Rabin-Karp algorithm. And what is this algorithm used for? When do you use it? How does this technique help me solve string-related questions? So this is very useful when you have 2 strings, one string t, which represents a long block of text, and a second string s, which is a search string, which may be smaller. So the Rabin-Karp algorithm, the key insight here is to use an incremental hashing function. So the naive approach is just to, whenever you match characters as you're going along T, you're going to match characters in S. But that will require you to iterate through S many times and may require you to go backwards on T. So incrementing rolling hash, what that means is let's put S through a hash function and get the value of, let's say, 52. And with this value, let's say there's 3 characters. So for T, for every 3 characters, let's put it through a hash function. If you get the exact same value, then boom, maybe there's a match. Since hash functions may have a collision, you still have to compare character by character. However, if the hash does not match 52, you simply go to the next 3 characters and compute that hash. These 3 characters compute that hash. These 3 characters compute that hash. So as you can see, this is a lot more efficient than comparing every single character every single time you start matching characters. So first technique, very useful at solving string-related questions. The second one that we're going to go over is the sliding window technique. And the sliding window, there's a few different flavors of this. And there's a few different data structures that you can use. So what is a sliding window? These questions are very often, I have one string S, and this string S can be however long you want it to be. And I want to find a window in that string S that matches some constraint. So what that can mean is I want to find the largest substring in S that has unique characters. Or I want to find the smallest window in S that meets some other constraint that has at least 2 A's, or at least 1 vowel. Whatever the constraint is, you have this string and you want to find a substring within it that maps the window. So the technique here is really that you are going to have these 2 pointers and you are going to incrementally, let's stick with an example. I think the most intuitive example is counting largest window with unique characters. So let's say that everything is unique except for these 2 characters, and all the other characters are unique. What we're going to do is we're going to incrementally increase our window with 1 pointer, and as we increase our window, we're going to have some set over here, and this is going to have all of our, we can use a hash set, we can use a hash map, we'll get into the details later, but at a very high level, right? We're going to increment this pointer, we're going to say, okay, is this a unique character by saying is it not in the hash set? And let's say the first one is a B, the second one is an A, the third one is a C. We keep incrementing, and then we hit A again. So we go to this pointer, we go here, we increment. So now our window is, this big. We've grown this big, and now we're trying to grow our window again. At this point, we say, hey, A is already in the set. So now the insight here is really, okay, well, let's move, starting from our other pointer, let's gradually decrease the window until we can increase the window again. So now this beginning pointer is going to go from here to here, and every time it moves, it's going to remove from the set add that character. So our B gets removed. And then now, our window is here, and we say, can we add this? And we say, hey, there's still an A, we can't add this. So now our window gets even smaller and it's only here. Our pointer moves, we no longer have our A, and at this point we say, okay, Now we can start growing again. The window grows bigger. The window grows bigger. The window grows bigger. And now 4 is the size of the largest window without unique character, or with containing unique characters. So sliding window technique, very common. You'll see it a lot on a lot of LeetCode questions. Linear time string matching, another very common, very useful algorithm to know. So the third one that I want to talk about, can we fit it down here? Maybe. Let's see if I can, we'll just move over here. We'll try to squish these in a little bit more. So the third algorithm that I want to talk about is a 2-pass algorithm. And a 2-pass algorithm, I'm sure you all have heard of this before and used it. This is basically whenever you have a string. I'm going to use some space over here so I have more. We have a string S, and that string S may have however many characters. And the traditional algorithm that we're using may be quadratic or be n log n, and we can't find a solution that's more effective than that. So the inside of the 2-pass is like, okay, what if we take a single pass through S, and as we're doing that, we calculate some state here, and this state is basically going to be maybe the occurrence of a certain type of parentheses, or maybe it's going to be, I don't know, we can create some external Boolean array or some external int array, or use a bit vector, or do some external storage, whatever that means. The second pass, as we're going through it, we simply use the data structure, whatever it is, a bit vector, an int, a count. We're going to use that combine as we're going through the string to compute our result. So the 2-pass algorithm is simply, can we get to linear time by taking 2 passes instead of 1? Or instead of doing some quadratic algorithm. So, okay, we've got there. The next one that I want to talk about, similar to 2-pass. Actually, before we go there, it's not an official name, but I like to talk about prefixing. And by prefixing, what I mean is really making a problem easier before I start. So, what do I mean by that? So let's say we have some string S again, and that string S has however many characters in it. And this problem is hard. I can't figure out how to do it in a decent time complexity. Well, what happens if before I even do anything, I sort it before? So now the problem becomes easier. Or instead of sorting, what if I reverse everything in this string? Or instead of reversing, what if I double the string? So all these are just different ways to make a problem easier, to prefix it before we even get started. And it's another very common technique for solving string-related questions. Okay, so moving on, let's go to the work backwards technique. So working backwards, this is super useful for problems that require you to be somewhat clever. And what I mean by that is, let's say we have some string S again. And in this string S, let's say, I've seen this a few times. And one is like, okay, let's say we have A, B, and maybe some empty space at the end. And they say for every A, replace it with CC, and for every B, replace it with DE or something, right? If we start from the beginning, we're going to erase characters. We're going to lose data, or we're going to have to use some external structure. If we start from the back, we say, okay, well, if I see a B, I can start here and maybe place my D here and my D here and move this pointer from here to here. When I see my A, I can now erase my B and put a C there. So as you can see, working backwards makes the problem a ton easier. Another use case is like for being clever. Like Roman numerals, if you work backwards, the problem just gets easier. So that's the technique of working backwards. Similar to working backwards, I think the sixth technique is the one that I think most people have seen the most, and it's a simple two-pointer algorithm. So a two-pointer, what that means is I have my string S, and to solve the problem, why not start from the front and the back and work in the middle, work towards the middle? Or I have my string S and I have 2 pointers at the front and they're gonna move at different rates, right? I mean, you see this for very naive algorithms too, where you just are going to move this pointer all the way this way until you hit some condition, and then you're going to move this, or maybe all the way to the end, and then you're going to increment this by 1, and then you're going to go it all the way to the end again. So that's just a use case of 2-pointer, but there's some smart algorithms where you start from the front, you start from the back, similar to working backwards, but you have 2 pointers and you work towards the middle together. This is probably useful like a palindrome, right? And it's spelled the same forward and backwards. Let's start from both sides and move to the middle. So the last technique that I want to go over is using additional storage. I'm just going to call it additional storage. And of course, there's a lot of different types of additional storage that, let's make sure I have space, storage, that I could get into: stacks, queues, hash sets, hash maps, all of that, sure. But, I'm going section by section, category by category, so I really want to cover stuff that is not going to be covered in other sections as well. So the types of additional storage for solving string-related questions, I like to pair this with a 2-pass technique, right? Like we were talking about, we take our first pass through and we calculate some state. One option is that state could be an array of booleans or an array of ints. Let's put this a bool. It's probably a little small there, or an array of ints. And what's a use case for this, right? So let's say I want to count unique occurrences, or unique characters inside of a string. If I hit, an A, I can represent in this int array, the first index of this array may map to some character, maybe the character A. If I'm talking about the English alphabet and I have A through Z only, I can count occurrences of A, I can count occurrences of B. If I'm using a bool array, I can say, have I seen this before, true or false? I've seen an A, I have not seen a B, I have not seen a C. That's just one, using additional storage. One that I feel is very important to talk about as well is a bit vector. So the bit vector is, let's talk about a similar problem. The similar problem is, do I have all unique characters in this string? Here, if I want to represent that with a bool array or an int array, I have to allocate all the memory for the array. I have to allocate, an int for times 26. That's a lot of extra memory that we don't necessarily need to use if we use a bit vector. What a bit vector is, let's take for an example an int. So an integer in, let's talk about Java, is 32 bits. So we have all of our bits, ... And similar to our int array, the bit vector in this int, every single bit inside of my int will represent a character. So A may be the 0th position. And since I have 32 bits here, I can represent the whole English lowercase alphabet pretty easily. So that's the advantage of a bit vector. I can accomplish the same thing, not all the time, but sometimes it can accomplish the same thing as an array with many ints, with a single int, and using bit logic. All right, so stepping back for a second, what do we have so far? These are 7 techniques, and let's step back even further, right? What I've done is I've looked at every question related to strings and cracking the coding interview and elements of the programming interview and the top 100 questions on LeetCode, and a few questions on Glassdoor as well. And what I've done is said, okay, with every single question, let's map it to a technique that's required. And these are the 7 techniques that I've come up with that will help you solve the vast majority of problems. So I feel they're very important to understand and will help you prepare and master the technical coding interview in a much more efficient way than just grinding through questions without thinking about the underlying techniques and underlying understanding that's required to solve them. So that's where I'm coming from. That's what I'm trying to do here. And the last thing that I want to leave you all with is a statement that I really believe in, and it is that learning begins where teaching ends. So think about that for a second. For you to actually understand these concepts, it is not enough for you to watch me talk about them. You have to actually solve problems and use them. Learning begins where teaching ends. So because of that, I've created the GitHub repo that is going to be linked below. And there are questions, the minimum set of questions that map to all of these concepts. So if you want to practice all of these concepts in a very efficient way, simply do these 11 questions. If you get them without using any help, without using any solutions, that's going to really, prove to yourself that you understand these core concepts that are at the heart of solving the vast majority of string-related questions. So thank you for listening, and if you all have any questions, leave a comment. Follow me on Twitter and leave a message there, or I have office hours as well. You're welcome to drop in and ask any questions you like. Thank you, and I'll see you later. Bye.